So it's the last one. Define what is the standard cell potential. It's basically the potential difference that you calculate between two standard electrodes. ठीक है, और standard is measured under standard conditions. ठीक है, that's what a cell potential is. अच्छा, उसके बाद you've got अच्छा, in this one you probably need the data booklet as well. So you're given complete a table with the substance used to make the electrode in each of these half cells. So what happens is that there are actually three different types of electrodes. You have if your electrode involves only ions, so what kind of electrode would you have? The electrode is going to be it's going to be a solution, and the solution is going to have both of these ions will be added to the solution. There's going to be cobalt 3 plus ions, and there's going to be cobalt 2 plus. And if it's standard conditions, so it's both of them are going to be 1 mole per dm cube, right? And what kind of electrode is going to be used in this case? Okay, if you just have ions, so you don't really have an electrode. So you're going to introduce an electrode, and that electrode has to be an inert electrode. Okay, anyone who likes to gain electrons or lose electrons, it's going to gain or lose electrons from this platinum electrode. Okay, so the first, this type of electrode is that it only contains ions. The second, so whatever potential belts, like cobalt ions, if they like to gain electrons, they're going to gain electrons from the platinum electrode, and the platinum electrode will become positive. If cobalt 2 plus ions want to lose electrons, they're going to lose electrons on the electrode, and the electrode is going to have too many electrons, and it's going to have a lower potential. It's going to have a negative potential. Okay? So that's the first type of electrode. The second type of electrode is that you have a gas. Now, when you have a gas, you would need a gas jar. So in that case, a gas jar is required. I'm just going to remove all of this. So a gas jar is required because Cl2 is a gas. So that Cl2 gas is going to be pumped into it. And you've got Cl ions. Cl ions will be part of the solution. So this gas jar will be part of a solution. And that solution will have a lot of Cl ions. As again, anyone who likes to gain electrons or lose electrons, it needs an electrode on which that will happen. You need to say, let me open this. So again, in this case, you will have a platinum electrode. And that platinum electrode, so anyone, if Cl2, in this case, Cl2 really likes to gain electrons. It's a very electronegative element, so it's going to gain all the electrons from the platinum electrode, and that will positively charged. Just a second. So both cases, it's going to be a platinum electrode. Or secondly, there's one extra electrode, which is that if the electrode reaction itself involves a metal, for example, iron, 2 plus gaining electrons and in equilibrium with iron. So in that case, the metal is going to be used as the electrode. So it's always platinum. Agar if the reaction itself involves a metal, then you're going to use the metal itself. Achha, next one is use data from the data booklet to calculate the E0 cell. So for this, you would need a data booklet. Okay. Each second, let me just Google the data booklet. Okay, I'm just going to. Cobalt 2 plus cobalt. Can anyone tell me what the electrode potential is if you already have the data booklet? Just
It's plus 1.82.
pretty good. Achha, so this one is plus the cobalt 2 plus, right? It's plus 1 point. Sorry, cobalt 3 plus and cobalt 2 plus electrode.
Yeah, plus 1.82.
Achha, what about this? This one I know. I think it's 1.36 volts, right?
Yeah.
Achha, now the rule is that the higher the potential, the greater the tendency for it to gain electrons. So simple rule electrochemistry, it's always that the higher potential gains electrons and the lower potential loses electrons. And the E0 cell is basically the potential difference. And technically, it's the reduction E0 minus the oxidation E0, or the way you calculate the potential difference is higher potential minus lower, that's 1.82, minus 1.36, and that's going to give you what? Yeah, what do we get? That's 0.46? What's 1.82 divided by 1.36? Each second calculator, that's
Sorry, 0.46.
this is 0.46 volts. And write an equation for the overall cell reaction. So one of the electrode is a cobalt 3 plus, cobalt 2 plus electrode. The other electrode is the Cl2, Cl minus 1 electrode, which is this one, Cl2 plus 2 electrons, and that's 2 Cl minus 1. This is 1.82 volts, and that's 1.36 volts. The higher potential always likes to gain electrons, and the lower potential is the one that's the one that's losing electrons. But before you make the overall reaction, you have to balance the number of electrons gained and lost. So if it's 2 electrons being lost, 2 electrons have to be gained as well. So make sure you multiply this by the first equation by 2. And then you add up the reactants. The reactants in the bottom equation is Cl minus 1, so it's 2 Cl minus 1. In the top equation, the reactant is 2 cobalt 3 plus. And the products that you have, in the first one, it's 2 cobalt 2 plus. And in the second one, it's the product that's forming is Cl2. So that's your overall cell reaction. So uske baad hai कि fuel cell is an electrochemical cell that can be used to generate electrical energy. So there's a methanol oxygen fuel cell can be used as an alternative to a hydrogen oxygen fuel cell. When the cell operates, the carbon atoms in the methanol molecules are converted into carbon dioxide. I said, now this is the oxidation reaction that's happening because electrons are getting produced. So he says, calculate the volume of CO2 in steam cube formed when a current of 2.5 amperes is delivered by the cell for 30 minutes. So it's basically simple moles and Faraday constant question. So there's a current that's flowing 2.5 amperes for 30 minutes. We know that Q is equal to IT is going to tell us the total charge. So the current is 2.5 amperes and the time in seconds is 30 times 60, right? So what do we get? 2.5 times 30 times
4,500.
ठीक है coulombs, right? I said then we're going to use the Faraday constant to convert that into moles because we know that according to the Faraday constant, which is 96,500, 1 mole of electrons in total have a charge of 96,500 coulombs, right? So if you have 4,500 coulombs charge, so how many moles of electrons are passing through the circuit? That's going to be X. So X is going to come out to be 4,500 divided by 96,500.
So it's
So how many?
0.047.
So that means the moles of electrons is 0.047 moles, right? 0.047 moles of electrons. And Nikala, you have to find the volume of CO2 now. So once I have the moles of electrons, I can use ratios. So the electrons, 6 electrons produce are in. I mean, the ratio between carbon dioxide and electrons is 6:1. So divide the moles by 6.047 divided by 6. How many moles do you get?
7.77 multiplied by 10 to the power minus 3.
7.
7 multiplied by 10 to the power minus 3.
Volume would be, and volume is at RTP, right? Room conditions. Make sure, otherwise you would have to use PV is equal to nRT. As a volume, you can calculate that 7.77 times 10 to the power minus 3 into 24,000. Okay, he's up. He's asking it in cm cube. So what do we get?
186.5.
Okay, so we're getting 186.5 cm cube. Okay, is this clear?
So sir, in this type of questions, we have to take care of the like significant figures like that. क्योंकि यहाँ पे तो 2.5 like two significant figures है ना?
So in this case, you can, just keep it 3 significant figures.
Okay.
Let me just double check. It's coming. I'm just going to check the answer in the marking scheme. Are they even worried about it? Okay, nahi, just 1 second. 9701 underscore is 20. Just 1 second. Just give me 1 second. So last question. The last question is, they're giving answer up till 3 significant figures. It should have been 2, like recently they've stopped worrying about it. Okay. I'm just trying to see ke, okay. 187. They're giving
So
187.
sir, we don't have to worry about the significant figures stuff like that in this paper in 2025. Like पहले तो उसके marks करते थे ना कि अगर आपका answer same significant figure
especially
आता था.
practicals. In practicals, it's important.
Okay.
Like recently, they've stopped worrying about it.
Okay, sir.
I said next one. So just keep everything up till 3 significant figures. I said previous question. Define what electron affinity is. So it's basically the tendency for an atom to attract electrons or to gain electrons, right? Okay, that's what electron affinity is. Nee, electron affinity. I saw. Sorry, इसको मैंने confuse कर दिया electron negativity के साथ. What is electron affinity? It's the exact opposite of ionization energy. It's the energy that's going to be released or absorbed when what happens? When 1 mole of
Sir,
gaseous
rather
atom.
than saying like energy released or absorbed, can we write enthalpy change?
No, energy release. Enthalpy change is normally the energy change. Yeah, energy release, not enthalpy change. Enthalpy has a different
Okay.
meaning. Like enthalpy,
Okay,
for example, enthalpy of formation, है ना? They're going to ask the meaning of what that means. ठीक है, so it's energy
Okay,
release or
sir.
absorbed when 1 mole of a of a gaseous atom gains electrons to form
Can you just say
form
energy change?
released or absorbed is basically energy change. And remember, electron affinity is, it can be endo and exo. The first one is normally exo. Oxygen can easily gain the first electron. Like, it's very hard for the second electron affinity. That's endothermic. Oxygen -1 would be, it would be very difficult for it to gain the second electron. Because it's already negatively charged, so there would be too much repulsion. So the first is normally exo, the second one is endo. So what is lattice energy? It's again, it's the energy that's released. Remember, it's when 1 mole of ionic solid is formed from its constituent gaseous ions. So 1 mole of ionic lattice is formed. Solid ionic lattice. And formed from what? Formed from its constituent gaseous ions. So this question is about the Born-Haber cycle. You have to probably construct the Born-Haber cycle. So starting with, energy cycle, the Born-Haber cycle, you have to construct that. Starting with, where's the enthalpy of nikalna? What are you looking for? We're looking for the value for enthalpy change of formation, right? Of Z in Br2. So we're going to start with the elements. The elements are zinc is solid and bromine is a liquid. And together they're forming now that's your delta HF, enthalpy of formation. That 1 mole of ionic lattice is formed from its elements. You got 1 mole of a substance is formed from its elements. That's enthalpy change of formation. So what are the steps? You atomize. I'm just going to, you atomize, and after that you're going to ionize, and you're going to turn it into ions. So the zinc has to be atomized, so it's going to become zinc, gaseous atoms. Simultaneously, the bromine, so zinc has to be turned into gaseous atoms. The bromine also has to be atomized, so it has to be turned into 2 bromine gaseous atoms. How do you atomize this? So what they've given you is, to get slightly trickier. The first step is atomize, right? Turn the elements into atoms. So zinc atomization is given, that's 131. So this path is 131. Now, how do you atomize the bromine? The problem with bromine is they haven't given me the atomization. They've given me the vaporization of bromine. So what I'm looking for is, I want to convert bromine liquid into bromine gaseous atoms, right? I want to atomize it, but they're only vaporizing it. So basically, what they're doing is bromine liquid, they're turning it into bromine gaseous atoms. So gaseous molecules. And that is 31 kilojoules, right? That's the value that they've given. Okay, but I don't want to stop there. I want to proceed further. I want to atomize it, right? So the next step after this is 31. So the next step after this would be that I'm going to break the Br-Br bond and I'm going to get 2 Br gaseous atom. So there's one thing missing. I want to go from bromine liquid to 2 bromine gaseous atoms. So I want this thing. How do I break the bond? So Jody, do you have the data booklet? What's
Yes,
the
I
bromine? What's the bromine bond energy?
193.
Yeah, that's 193, and you're breaking only one bond in the bromine molecule, right? So this step actually broke down into 2 steps. the first thing was vaporization, because normally they don't, in the Born-Haber cycle, they don't use vaporization. But that's just bromine liquid evaporating and turning into gaseous molecules, and then I broke the bond. So basically, I ended up at the same point. So this step is also 31 plus 193. Okay, so I've atomized zinc in one step, and I've also atomized bromine in the same step. Ye clear? Is this thing clear? But is this clear? Yes or no?
Yes.
Or, and after that, you have to ionize it. So now in one step, I'm just doing all the things. Zinc has to lose 2 electrons, and the 2 bromine atoms they have to gain 2 electrons. Okay, this is gaseous and this is gaseous. Now zinc ionization is again in the data booklet. So can you tell me what the ionization of zinc is, the first and second?
908 and 1713.
98 and 17?
908 and 1730.
908 and the other one is 1730, right? For bromine, the electron affinity is given. That's minus 325, and that's going to be minus 325 times 2. Now, once I have this, the last thing I'm going to do is I've got ions. I can join the ions and I can form the lattice over here. So that's the last step. And the lattice energy is also given. That's where is it? This is the lattice energy. That's minus 2678. Now you have to review everything. This cycle that we drew. We atomized. We ionized. And then we joined the ions together to form the ionic lattice. So my path is pretty clear. What I need to do is I have to go all the way and reach this point. So that's okay. So that's what needs to be done. And you have to be very, very careful when you're, you have to double check this, that are the moles done correctly or not. Zinc was atomized. The bromine was vaporized, 31, and then the bromine bond was broken, that's 193. There were 2 bromines gaining electrons, so that's minus 325 into 2, and then there were 2 times 2 electrons being lost from zinc. So everything looks fine. So I'm going to look at delta HF now and calculate it. One path is equal to the other path, so it's 131 plus 31 plus 193. And after that, it's plus 908. Then it's plus 1730. And then it's minus 325 times 2. Make sure the arrows are in the right direction. And then it's minus 2678. So you calculate, what do you get for this?
Minus 335.
Okay, so it's minus 33. It can't be 3 numbers. It's got to be a bigger value. Is it minus? That's it? That's
Yeah.
fine. So we're not calculating lattice energy. We're calculating delta HF. So we're done. That's the enthalpy change of formation of bromine. Then he says, why there's a difference between the lattice energy of ZnBr2 and ZnCl2. So basically, you have to explain why this is larger, right? And you got ZnBr2. This one is more exothermic, right? So when you're forming this lattice energy, why is it producing more heat energy? Why is it more exothermic? And the answer to that is that it's a stronger lattice. And so it's a stronger ionic lattice with stronger ionic bonds. And why is it a stronger ionic lattice? The answer to that is that Cl ions have a smaller ionic radius. And greater charge density. Okay, so the smaller the ion, the greater the attraction, the more tightly packed they're going to be. So the ionic bonding is going to be a lot stronger. So which is why it's a stronger ionic lattice. And then the next one, explain why there's a difference between ZnCl2 and ZnO, which is kind of going to be, ZnO is like a lot more exothermic, which means ZnO is like a really strong lattice. And what's the reason for that? It's kind of the same because the only difference is the oxygen ion. You got greater charge. So there's going to be more attraction. Cl is -1, while oxygen is -2, right? So you got a greater charge, plus it's a smaller ion as well. So both factors count. So which is why the oxygen ion over here has greater charge density, right? And you're going to write that this forms a stronger ionic lattice because of these factors. Okay, is this clear? This question? Was the previous one. This one is about, this is summer 20, right? That's the previous one. So you got question number 6, and this is about polymerization. So describe the type of polymerization that's shown over here. Now this one is definitely, remember, I'm just going to describe all the polymerization. There's condensation polymers and there's addition polymers. Addition polymers is alkenes making addition polymers, which we've already studied in AS. Condensation polymers is that there's either polyesters, which is that you have an alcohol and a carboxylic acid. And the two are going to react together. The OH from the carboxylic acid and the H will react. And they will form an ester link right in the middle. Which you can see in the above reaction. You've got an ester link over here. The same polyester can also be formed if you replace the carboxylic acid with an acyl chloride. So even in that case, the OH from the alcohol and the Cl are going to get knocked out, and the double bond O will connect with the oxygen. So polyesters are formed when you have diols reacting with dicarboxylic acids or diacyl chlorides. And then you have a similar one, which is polyamides. Polyamides are, again, you have only this monomer changes. Over here, you either have a carboxylic acid or an acyl chloride. And let's say I have an acyl chloride. Amides are going to be formed when you have the amine group on the other monomer. And the H and Cl are going to get knocked out, and the Cl bond O will connect with. So that's it. Those are the only two types of condensation polymers that are going to get formed. So the answer to the first one is it's obviously a condensation. The next one is draw. He says that Nalgene is a. I don't know what Nalgene is. What is Nalgene? He says Nalgene is a polycarbonate formed from the diol P. So I have no idea what is diol P. And this thing. So sorry, diol P is this thing. So we've got diol P and we've got, he says draw one repeat unit. Now this one is clearly an acyl chloride. So drawing the whole repeat unit in this case is going to be, it's going to take time because you have to draw this. You have to draw this entire molecule. So we're going to try and draw this molecule quickly. Okay, so it has 2 benzene rings. It's got 2 benzene rings and it's got the rest of the stuff, which is so you got 2 CH3s and you've got an OH and you have an OH here. Plus there's a benzene ring. So I've basically drawn the ऊपर वाले के साथ ही कर लेता. As I've redrawn the molecule. And he's saying draw the repeat unit with this thing, COCl2, right? Which is C double bond O. And you have a Cl. There's going to be another one over here, C double bond O and Cl. And what will happen is that the OH and H are going to be lost. So the H and O will be lost. And so the H and Cl will be lost and they're going to connect together. Condensation or elimination happens in the middle. And they join up. And this thing repeats on the ends as well. So they're going to go away as well. Now you're being asked to draw one repeat unit. The repeat unit is basically, if you start from this point, so when does it start repeating again? It's probably going to start repeating exactly at this point. The whole thing starts repeating and you're supposed to only draw one repeat unit. So I'm going to rub that off. And then he says, identify two types of intermolecular forces that are responsible for these properties of Nalgene. So it's strong and it's a tough polymer. So what are the two properties? And what are the two properties for this? Why is it strong and tough? What are the intermolecular forces? The first one, it's a polar molecule, right? It's got permanent dipoles. So that's the first thing. The other one is that it definitely doesn't have hydrogen bonding. The only thing that's other than this is that it's got van der Waals forces or instantaneous dipole. इसको पूरा करके लिख लेना. Instantaneous dipole induced dipoles. Or bracket में you can write van der Waals. I said complete the table to show how the secondary and tertiary structure of the protein is. This is no longer in your part of your course, so we can skip that. The DNA is also gone. State, but DNA basic is there, but the other part is all gone. I said many polymers are degradable. State two different processes by which some polymers can be degraded. So, what are the two processes by which polymers degrade? Okay. One of them is that it's
Hydrolysis.
that's hydrolysis. So, what is the other one apart from hydrolysis? Yeah, also, then what are the other processes by which a polymer degrades? ये याद रखना कि
Is it acid or no, but that comes in hydrolysis as well.
I mean, remember this thing always. Okay, the main process by which pretty much all organic molecules they degrade naturally. Not the main process. My heat we are like not the main process actually. Forget the main process. It's UV light. Okay, there's a lot of things happening. Molecules when they go into the upper atmosphere, they start breaking down. TE or CFCs, etc., they all break down because of UV light. TK UV light, that even causes skin cancer. Our organic molecules, they also start breaking down because of UV light. So sunlight basically breaks it down. That's the next one. So you've got this molecule. He says that it's broken into its mono by heating it with. So hydrolysis is happening. So he's saying the amino acid, THR, and two other organic products are formed. So what's the question? What are the structures of the two other organic products? So one of them is given. Now all the ester and amide links are going to break. Okay, this over here is an amide link. So I'm going to break all the amide links. ठीक है, amide हैं, there are no ester links. This is an amide serial bond O with NH. अच्छा, what else? At the bottom of this one is an amide link, and this one over here is an amide link. See, the tricky part is that, remember, this is not an amide link, because you've got a serial bond O, and then you have a CH2. So this is not an amide link. Okay, so you have to identify it's NH right next to a serial bond O. NH right next to a serial bond O. Okay, so don't always break the bond that's exactly between NH and serial bond O. उसी तरह ना, remember, this over here is not an amide link. It's a serial bond O, which is not next to an NH. NH comes after that. So this is, remember, this one over here is not an amide link. So the tricky part in this question was, okay, they had kind of mixed up the NH and serial bond O. So you have to identify, okay, NH has to be right next to a serial bond O. That's what an amide is. So this is an amide link. This one over here is also an amide link. So I guess that's about it. And what happens when you have the double bond O turns into carboxylic acid, and this becomes NH2. This becomes NH2. This becomes a carboxylic acid. This is NH2. NH2, and this is I said, so two other organic products. Which one is this one? Which one is this, by the way? But is it getting formed? I think it's this one, right?
Yeah.
Okay, there's a 1, 2, 3 carbon atoms. So it's 1, 2, 3 carbon atoms. The third one over here has both carboxylic acid and H2. And you've got an OH on the second carbon atom. Okay, so that's it. I said two other organic products. So one of them is this. And the other one is obviously this. I think these are the two other organic products. This and this, they look exactly the same. This is going to be carboxylic acid. Okay, so is this clear? You found the two other organic products. Okay. I said then your three-letter abbreviation that's not in your course, so we can skip that. I said name two analytical techniques that could be how are amino acids separated? Yeah, what is the process called?
Electrophoresis.
Okay, and any other way that they get, so you got electrophoresis, right? Any other way? I mean, think about O levels. Like there was a
Paper
technique with
chromatography.
paper chromatography, but that's not part of A levels. A levels, where what chromatography did you study? You studied two types of chromatography. There was something which was very similar to paper chromatography, and that was
Thin layer.
it was thin layer chromatography, where you have, instead of a paper, you actually have a gel that's coated onto an aluminum sheet. Spelling a chromatography, right? The thin layer chromatography, that's going to be used. So we're done with the question number 5 now. Okay, question number 5 is again organic. It's about partition coefficient. What is partition coefficient? It's the ratio of solubility of a dye in two different immiscible liquids that don't mix. So that's what KPC is. And then there's a question of so there's KPC. Benzoic acid is the solute, and the two liquids are octane 1-ol and water, right? So I'm going to draw a diagram. It's going to have octane 1-ol and water. So, so there's octane 1-ol. Let's say the top layer is octane 1-ol. And the bottom layer is the water layer. Benzoic acid, I'm just going to call it X. So benzoic acid and the KPC value is given. That's given as 79.4. Now he's adding 0.4 grams of benzoic acid to the octane 1-ol and it's shaken with 125 cm3. So initially 0.4 grams go into the octane 1-ol layer and the volume is 25 cm3. And he shakes it with 125 cm3 water. So what will happen is that some of the benzoic acid will travel and cross the partition and it will mix with the water. The water what is the amount that's going to go into the water? We don't know. So I'm going to call it X grams. So what is the amount of benzoic acid that's going to be left in the upper layer? That's going to be 0.4 minus. It's going to be 0.4 minus X. ठीक है, ये clear है? This part, is this clear?
Yes, sir.
Now what you have to do is calculate the mass of benzoic acid extracted into the water layer. So basically you have to find X. We know KPC. We already know what the value is. That's 79.4. So it's octane 1-ol layer divided by the water layer. So it's how much of it is dissolved in the octane 1-ol layer? That's 0.4 grams minus X. In how much cm3? That's 25 cm3. And divide that by the water layer. What is the water layer? That's X grams in 125 cm3. So 25 and 125, what is that? That's 1 and 5, right? So I'm just going to simplify things a bit. So what we have is 79.4 gets multiplied by X divided by 5. And we'll get rid of the 5 as well. It's 0.4 into 5. What is 0.4 into 5? That's 2 grams, I think. Minus 5x. And bring the x to the other side. So it's going to be, so it's going to be, let's go solve quicker. What do you get for this? 5 into 0.4, that's 2, and 5x, that's 5x. You bring, get the x's on one side, 79.5x plus 5x, and that's equal to 2.
I'm getting 0.0237.
So that's
0.0237.
Which is very small, but it kind of makes sense. Because if the KPC is 80, right, that means the benzoic acid over here is 80 times more soluble in the water. So not a lot of benzoic acid is going to enter the water layer. So if you had 0.4 grams, a very tiny amount is actually going to go into the water layer. The working clear? Is that part clear?
Yes.
Yes, sir.
So next part is that you have KPC of there's another thing. Again, it's this. So the
Is there
KPC of
we always have to divide, like for example, whatever octane 1-ol divided by water. So water should always be the like the denominator?
Normally water is the denominator. KPC values are normally called. I mean, the first thing that appears in the statement, that's the numerator, and the second one is the denominator. Or the default state is that the water is always the denominator. Okay.
Okay, sir.
So now, so this is, for example, over here, it's again octane, 1-ol, and water, right? But you've got a different solute now. Now this solute is going to have a different KPC value. So obviously you have a different solute. So some solutes will be more soluble in one layer, some of them will be more soluble in the other layer. Now the question is just a 1-mark question, but it's a tricky question, which is that the KPC of benzophenone is different from the value. So it's a simple question. They're not even asking whether it's higher or lower. So you've got, and this is benzophenone, right? So I'm actually going to ask this question. Okay, I've got benzoic acid. I mean, there are two different solutes. And then there's this benzophenone. That's like, if you look at it carefully, it's like a ketone group which has C6H5 on both sides. Out of the two solutes, which one do you think is more soluble in water? Based on the intermolecular forces.
The benzoic acid.
Yeah, because it's got OH groups, right? So this is more soluble in water, right? So that means if I have this container over here, okay, so if I have this container over here, more benzoic acid is going to be found in the water layer, right? So that means you're going to get a smaller value of KPC. Okay, this is the numerator and this is the denominator. So if you have more of the salt or the solute dissolving in the water layer, the denominator becomes bigger, and which is why you're going to have a smaller value of KPC. This one over here is relatively more non-polar. So if it's more non-polar, it will be more soluble in the octane-ol layer, the top layer, right? So the numerator is going to have a bigger value and the denominator is going to have a smaller value, and the KPC is going to be a lot bigger, right? So this one is going to have KPC, which would be relatively large. And this one will have KPC, which is going to be relatively small, right? So, but is this all clear?
Yes, sir.
Yes.
But they were not, I mean, I just made the whole question up. They were just looking for a simple answer, which was why are they different? So the reason is that benzophenone has a different solubility in the water layer and the octane 1-ol layer compared to the benzoic acid. So which is why you're going to have a different KPC value. That's the next one. You got an organic question and says that, so you think benzophenone can be synthesized from benzoic acid in 2 steps as shown. And so basically you have to make these 2 steps up. Now, this thing, one of the reactants is probably going to be benzene. And this is acylation that's taking place. Because the other one, this one over here, this one over here, the carboxylic acid is probably going to be in the form of an acyl chloride. Because once it is in the form of an acyl chloride, the carbon becomes very, very positive, and it will very strongly get attracted to the benzene. And the Cl and the H are, from the benzene are going to get knocked out. And this serial bond O would then eventually, this serial bond O would then eventually join with this benzene. So you're going to get this molecule over here. So you had to think about this, like how do you go from carboxylic acid all the way? So you had to think that the carboxylic acid probably got converted into an acyl chloride. How is it getting converted into an acyl chloride? It's going to be PCl3. plus heat. And how does acylation happen? You need an AlClC catalyst for that. Okay. So is this clear, this reaction scheme?
Yes, sir. And sir, secondly, like in J, the position of the COCl, it should be the same as in like benzophenone.
Nikhil, it
Yeah.
doesn't really matter what the position is, because it's I mean, there's nothing else attached.
Okay.
So we did talk about the reagents as the next one. Now again, there's a different process that's happening, and I don't know what that process is. So what's happening here? I said this is KMnO4, right? So I have to think in reverse now. KMnO4 is an oxidizing agent. So I'm going to because this is a lot more confusing. So this is an oxidizing agent, and you got a ketone over here, right? So if I go back, then what should ideally happen is that it must be like if you reduce a ketone, what should you get? You should probably get an alcohol, right? I mean, it should probably be an alcohol. So let me just draw the
Sir, but I have a question in L, like they didn't write O, so it's only C13H12. There's no O.
how
So how
wo
yeah.
about now that is something that we have to think about. Like, but if it was up to me, I am going to go for this thing, which is wrong at the moment. Okay, I mean, I'm just making guesses, right? But is this part clear that this is a possibility, right? And तो अब सोचो कि C13H12, where are we stuck? Because C13H12 is a completely different thing, right? So how do we go and reach L? That's the question. And the trouble is, because that's probably the only thing that makes sense. Apart from, or we can move from this part as well, because I need to attach a benzene, right? What I can also do is if I try to think of it in the forward direction, because remember, this question is entirely guesswork. Now, this is alkylation. The carbon over here is positive. So this positive carbon, जो यहाँ पे, this positive carbon over here, it is going to get attracted to the benzene, and the Br is going to get knocked out. So if I go in the forward direction, the only possibility is that how do you go from a halogenoalkane to two benzenes, right? The only possibility in that direction is that the two benzenes, if I just copy it, okay, so the other possibility is that you're not going to have an OH. It's just going to be carbon with two H's. Because this carbon over here, ये वाला जो carbon है, this one will go and attach to the other benzene. Okay, that's like alkylation. That's like carbon chain getting attached to a benzene. So forward में I'm getting this. And if I think of it in the backward direction, I would probably go with this. I said, now based on the formula that you have, which one is it? C13H12. I mean, this is C13. 6 benzenes. C6H5. C6H5. And then there's a CH2 in the middle, right? So how many hydrogens do you have? 12 हो गया ना, C13H12. So the best guess I can probably make is this one. You clear? Is this part clear?
Yes.
because this one, the OH does not make sense. Okay, now how did it got converted to this? They're probably not going to ask because we don't know how that's happening. It's a reaction that's not part of our syllabus. But the first one, the second one that I drew, that looks exactly like C13H12. So he's saying deduce the identity of compound L and draw its structure, which we did. Name the mechanism of step 3 and suggest step 3. I mean, this step over here. So name the mechanism. Remember, benzene reactions are all electrophilic. Substitution. And both for alkylation and acylation, what you need is, you would need the catalyst AlCl3. Sorry. You would need AlBr3 because you got bromine. Bromine is over there. So it's going to be AlBr3. And the other part is, you would need conditions. AlB3 would be the catalyst. You can add heat. And the other reagent that you would need is another benzene. Okay, so is this question clear that this, remember this question is more guesswork. It's the first reaction is definitely part of our syllabus. The second reaction, we have no idea what that's doing. Okay? But the good thing is they're not really asking any detail about the second, this step number 4. The only thing that they're asking is what type of reaction it is, which it clearly is an oxidation reaction because you've got KMnO4 reacting with it. Okay, is this clear?
Yes, sir.
बस ये जल्दी से ना इसका last part कर लेते हैं. Reduce the number of peaks of benzophenone. Where's benzophenone? It's this one, right? So the number of peaks. So starting with the first one, this and this one is slightly tricky. These two are exactly the same. Okay, that's your first peak. You clear that these two have exactly the same chemical environment. I said these two are exactly the same. And they're exactly the same as these two, right? So that's your second peak. All these carbon atoms are exactly in the same environment. As the next one, this carbon are exactly the same. And they're also exactly the same as these two carbon atoms. So this is my third peak, right? I said these two are, your next one and these two are exactly the same. So that's your fourth peak. Over there's one unique one that's over here. That's your fifth carbon. So there are 5 different carbon environments, and you're going to have 5 different peaks. You clear? Is this thing clear? Or we can identify
Yes,
2 different environments of carbon atoms that would result in different chemical shift ranges. To get 2 different chemical environments you have to identify, which are going to give you 2 different chemicals. You just have to look at the data booklet. If the data booklet now is going to be printed next to it, I'm just going to label this. This carbon over here is going to have a completely different environment, right? You can look at the data booklet and figure out what the chemical shift value is. So it was RC double bond O, and there was a carbon chain on the other side, right? So this is one environment. And what's the other environment? The other environment is the benzene carbon atoms, right? All these carbon atoms are part of benzene, right? So the other environment is values you can look up in the data booklet and see what the benzene carbon atoms, how do they resonate? How does a carbonyl resonates, right? You can just copy the values from the data booklet, ठीक है? चल ठीक है, कल continue करते हैं. We're out of time, ठीक है, and we are done with the fourth question. Sorry, the fifth question. So the next 4 questions we'll do tomorrow, ठीक है? आवाज मुझे नहीं आ रही किसी मुझको